All right, our next example here is example 3. We are to determine the volume of the solid generated by rotating y equals 2 square root of x about y equals -4 for x between 0 and 2. So this is an interesting problem, one for just how it's worded, and two, it is an example, our first example of a problem where our axis of rotation is something different than the x or y axis. Our axis of rotation is actually going to be down here. It is a shifted axis. This is y equals -4. We say shifted because while it's not the x-axis, it is parallel to the x-axis. It's been shifted. So this is an example of a shifted axis. So this is a shifted axis example. All right. So now let's draw our graph. Our graph is just twice as tall as the square root of x, so I'll just draw an extra large square root of x. And we're going to go from x equals 0 to x equals 2. So x equals 2 is right here, so let's just say it's there, I'll draw a vertical line. And maybe I need to make this, I'll draw this down through our, I'll draw this through our axis of rotation. There we go. So now what we can do, okay, so from 0 to 2. In this problem, it doesn't specifically say if we should include, is it this region here, or is it this full region here? So if they don't specifically say, but they at least are mentioning about an axis, you can assume that your region then touches that axis. So I'm going to go ahead and run with that assumption, that this region touches our axis of rotation. So that means if I outline our region in blue here, that is what's being rotated about that axis, y equals -4. So in order to do this, it's a little bit different than what we've done, but it is more or less the same thing. There's just one extra little step we have to do. So because we're rotating about a horizontal axis, that means our volume integral will be with respect to x. So we'll have pi integral a to b radius squared dx. And since we're integrating with respect to x, we just need to say what's the leftmost x value. Well, that's 0. And the rightmost x value, that's 2. So a and b become 0 and 2, respectively. Now the radius is going to be a little bit more, a little bit different to calculate here. Kind of. The radius, as we talked about in the previous video or example, the radius is always measured from the axis of rotation. So I'll just pick a representative x value, something between 0 and 2, and I will sketch a line to our curve. This right here, it is not tethered to the x-axis, so I cannot call this full length. I can't call that y. Can't do that. It's not a y. It's not tethered to the x-axis. But we can relate it to y. So for instance, y would be this distance. So here I'm just going to put a little dotted line here for a moment because we're right there. This distance right here, that is y. And we know what this distance is. This distance right here is 4. So clearly the distance is 4 plus y. So our radius, r, is 4 plus y. So r equals 4 plus y. And what's the relationship between y and x along this curve? Well, it's y equals 2 square root of x. So this would be 4 plus 2 square roots of x. So then we need to know the radius squared, so this one just is a little bit more algebraically. This would be 16 plus, let's see, 16 square roots of x plus 4x. That would be the, if we FOILed that out, if we expanded that out. So our volume becomes pi times the integral from 0 to 2 of 16 plus 16 square roots of x plus 4x dx. There's no special techniques of integration here. This is just straight up power rule for integration. I'm happy in these videos to show the integration for integrals that are maybe a little bit more complicated or integrals that require Calc 2 specific techniques of integration. But anything that's a Calc 1 integral, it's not really worth the time in the video to go through it. So the final answer for this one is simplified and polished a little bit, the final answer. This is pi times the quantity 40 plus 64 square roots of 2 over 3. That's the volume for that region.